All right, folks. Please mute yourself. We are going to do this paper, which had quite a bit of impact. And in a way, it's the bridge from a large language model like a GPT-3 to something like ChatGPT. How do you go from one to the other? Now, you have, I hope, in the 3 hours in between, learned about fine-tuning any model. When you fine-tune any model, you align it you make it serve a purpose. For example, for text classification, we did fine-tuning using just a plain PyTorch last week. This time we used, or you went through the tutorial of using Hugging Faces to do the same, right? You could do that. There is a special kind of fine-tuning that you can do to large language models specifically that makes them much more aligned to human conversations and human intention. And this paper is about that. It introduces the concept, the very important concept that came about of InstructGPT. Okay? Now, let us capture what you, and I think in taking the short course with deeplearning.ai, some of the territory they have covered. So I'll be a little bit fast and go over it. So the main problem is if you take a vanilla pre-trained model and fine-tune this, if you ask it a question, or the typical question that you ask is, what's the capital of France? It might repeat, what is the capital of, let's say, Germany? Now, it is a pretty good continuation, logically speaking, as a probabilistic thing. It's quite likely and a good output. It's meaningful, but it's not what you would have wanted. It needs to understand that a question should be followed with answers. So how do you do that? That is the instruct fine-tuning machinery that this paper introduces. The core of this, what it does is this image that we'll talk about. So it first introduces the concept of alignment, which I think is very important. What is alignment? Human alignment. And typically it is quantified as 3 values. One, that it should be, well, obviously the first thing is that it should be harmless. 2, it should be honest or truthful. And the third is, it should be helpful. So when it answers a question with this, then this condition is violated. That is not. Whereas if it were to answer it by saying Paris, then all the 3 conditions would be fulfilled. That is one aspect to it. The other aspect is when you pre-train a model, you have trained it on the web data. Web data is, there's a lot of toxicity in the web. And that toxicity will get you to violate the harmless part also will get violated. And lastly, the pre-trained model displays a considerable ability to simply hallucinate or make it up because it's a next word prediction model. It has no notion of the truth. So what it does is it says, okay, what is a good next word that I can produce, and the next word. And so in one of the benchmarks, they show that GPT-3 displays a 41% of the responses are hallucinatory. Okay. This was the findings way back. So it seems to be therefore violating 3 critical conditions for alignment to human expectations. human values. So now, well, not human values. Human values is far harder to quantify, and they go into that. But they say human expectation. Let's try to align it to what we expect. Now, the main journey of fine-tuning we'll go into in a moment, but let's read the summary of the paper carefully, and then we'll make progress. Making large language models bigger does not inherently make them better at following a user's intent. For example, large language models can generate outputs that are untruthful, toxic, or simply not helpful to the user. So you realize that these three conditions, they are the antithesis of the alignment thing that we noted down. Right? In other words, these models are not aligned with their users. In this paper, we show an avenue for aligning language models with user intent on a wide range of tasks by fine-tuning with human feedback. So it is not just fine-tuning, but it is also doing it with human feedback. And that's the RLHF part that is in addition to just fine-tuning, supervised fine-tuning. So starting with a set of labeler written prompts and prompts submitted through the OpenAI API, we collect a data set of labeler demonstrations of the desired model behavior, which we use to fine-tune GPT-3 using supervised learning. So what does that mean? See, what happens is that you can get a bunch of human beings, the labelers. Labelers are real people. So these labelers are there, and you can sit with them and you can create some prompts. You say, here's a prompt, and here's the ideal response. Right? So this is as close to creating ground truth labels as you can get. You can say, this is what you would expect. Right? And the other thing you do is that they had an application, GPT-3 was being accessible through an API. As you know, this is the history of it. It's too big a model. They didn't let people to download. They exposed an API. When you use the API, you would get a lot of requests, input requests, right? Input prompts, and then for a small quantity of them, they did get permission to harvest those prompts and the responses. Right? So in both these cases, what you end up with is prompts and responses, and you get that. We collect a data set of labeler demonstrations of the desired model behavior, which we use to fine-tune GPT using supervised learning. Supervised learning would mean, okay, now you attach the normal loss function and go at it. We then collect a data set of rankings of model output, which we use to further tune the supervised model using reinforcement learning. So after you have fine-tuned the model, so let's take the first step. You pre-train. You take a pre-trained model, which is done. Then you supervise fine-tune it. Once you supervise fine-tune it, what happens is that, and this goes back to the fact that at the tail end of a LLM, there is a softmax function that you sample out of. So what you can do is, even after supervised fine-tuning, you can produce a whole variety of responses, right? R1, R2, R3, R4, R5, let's say, and they are presumably superior to, let's say, bad responses, B1, BK. Right? These are the pre-trained model are hopeless, relatively speaking. But you get, after supervised fine-tuning, you get slightly better responses. Now what do? You have people sit and rank those responses. You ask them, which of these is the best, is a better response. And you can do it like that. Or sometimes what happens is, if you look at the UI, this would be the input. It would produce two outputs. And user has to click either this or this. Right? Some judge has to, human feedback can come just as pick the better answer from these two. Right? And you pick it, and that's how you end up. In reality, that it turns out human beings are pretty bad at ranking. So the way you do that is you give the same input and response, and you ask different users to prefer one versus the other, and then internally you convert it into a score, and therefore a ranking between that. So that's what they do. So that is what they're talking about. So they say we then collect a data set of rankings of outputs, which we use to further fine tune the supervised model. Now, once you have these rankings, you use something called reinforcement learning. Now with human feedback. Why? Because you just gathered human feedback. Because to these responses, the moment you associate a score, right? To each of these, obviously you have given human feedback on the outputs that you generated. Now what you can do is try a reinforcement learning. So a little bit about reinforcement learning that I'll go into. Right? Now, I must also say that, guys, this paper is an old paper. It started a lot of things. As you know, very recently, we covered the direct uh, uh, preference optimization paper, which basically you don't need to create an explicit reward model. It implicitly creates one, right, hidden. And so you don't need the machinery. I mean, you don't directly need some of the pieces that this original paper starts out with. And it uses a PPO, a proximal policy optimization. But today, we wouldn't use that. I suppose we would use DPO. But we'll go along with this paper for the time being. So in this paper, they point out that compared to human evaluations of the various models on our API prompt distribution, evaluated by how often outputs from each model was preferred by those from the 175. And you notice that the PPO prompts are usually winning the game, right? It's at the top of it. It has a very high win rate, right? And what was remarkable, as they point out, that even when they took a model that was much smaller, much smaller by 2 orders of magnitude, 100 the size of the model, most of the time it would still beat the full GPT-3. GPT-3, for reference, in those days was 175 billion parameter model. And what they are saying is that this, our InstructGPT model, and this statement is crucial, as well as variant, trained without pre-trained mixed BPO significantly, training mix BPO significantly outperforms the GPT-3 baseline. Outputs from our 1.3 PPO PPT, which is that you do the PPO, models are preferred to those of the error bars through the paper, 95% confidence interval. Anyway, we'll come to that. But what is the main thing that this paper does? See, you collect demonstration data and train a supervised policy. Let's go over this paper. And this figure, by the way, is the celebrated figure of this paper. So there's a lot going on here, and I'll go over this a little bit more carefully. Step 1, collect demonstration data and train a supervised policy. A prompt is sampled from our prompt database. So you take your prompt database. And the example here is illustrative. You say, explain the moon landing to a 6-year-old. So what would happen in real terms is that if you gave it to the unfine-tuned model, if you just gave it to the pre-trained model, it would just say, explain the moon, explain this. It would just go on repeating it. So when it does that, it is producing very likely continuations, right? Because it is behaving like a stochastic parrot. At that particular moment, it doesn't know that you're expecting an answer. You need to train it. And the whole thing is that you train it to human expectation that, hey, I'm not asking you to just parrot back in different ways what I just said. I want you to, or something similar, but I want you to answer this question. So then what happens is, and this is the thing that is crucial, you have a human being, at that moment, a labeler, which is a human being, write an answer. They say, some people went to the moon, blah, blah, blah. Now, what do you have? As we said, now you have the X, Y, the input and the ground truth that you would have liked to see. This is used to fine tune with supervised learning, right? So you can do your standard supervised learning fine tuning with this. So at the end of it, what would you end up with? You would have a SFT trained model at the end of step 1. What do you do now? collect comparison data, and train a reward model. So this will take us on a quick digression through reinforcement learning. I'll keep it very brief and simple, but because we don't want to get too deep into that at this moment. A prompt and several model outputs are sampled. So this is what I was saying, that you can take a prompt and you can have, did I do that here? Yeah. You can get many different outputs. So you do that. So let's take this. You get, in this picture, as you can see, you get A, B, C, D, E. And then labeler ranks the outputs from best to worst. So actually today, we don't really ask people to rank, because ranking, it turns out, people are terrible at. Right? So what you do is you just show them two and ask which is better. And gradually you extract a rank out of it by comparing the overall score that each response got across the different labelers. So this part is a little bit, but anyway, the end result is that you have a ranking of the responses. Now, this data is used to train a reward model. So that needs explanation. So imagine that imagine that you take a small reward model. So what is a reward model? Imagine that you take a small model, much smaller model, let's say 10. I think this paper will talk about what size that model is. I think it is either 2 billion parameter, 2 to 10 billion parameter model, a tiny model compared to the GPT-3 itself. You take that, and actually sometimes, well, one of the things people would do, okay, you take this reward model and you try to make it learn this behavior. Given prompt, this give more reward to A, let's say that to D, in this particular D, C, A, B. So produce your rewards, different degrees of rewards for all of these. So you can train a model to do that. And when you do that, it knows, like, hopefully, how to reward, how much to reward a system or a given response. That brings us to the core part, the policy, the policy optimization. See, the way the reinforcement learning works is, and a very quick primer of the reinforcement learning. You don't give any instruction. You say, here's a box, produce an output. So you produce a Y hat. Right? And generally, it's a more complicated than that. It's a multi-step process, but we just take it as that. So you produce a complete response, and then a reward function will come and associate a reward to Y hat. It will say, okay, you produce this. This is the reward you get for that. So then what happens is you have another machine that you have trained, that you have on the side, another network. This is the policy optimization, the PPO. What it does is it looks at this. It says, hey, I'm trying to maximize reward, right? It is a policy optimization. What is a policy optimize my optimization? What its purpose is? It's an engine that will tell the machine. So the way it will work is that input will go in, something will come out, it will go here, and it will tell what output to produce next. What would be a better output, right? Because it is learning from the reward. The reward system is giving it a certain degree of rewards for the output, and its job is to reverse engineer the reward framework and basically build a model. And those models, the good thing is that they're differentiable. You can do the standard gradient descent and so on and so forth. And so it figures out and aligns it. And that is the whole process of reinforcement learning with human feedback. It's very interesting that you do that. There's a very lovely cartoon that I saw. It was a meme going around, and where did I see that? Okay, I'll remember that. But it was there, I believe, on Twitter. Somebody forwarded it. It showed that the pre-trained model produces a big monster, big ugly monster. It trains it. Out of that ugly monster, through supervised fine-tuning, you produce a smaller monster, a little bit more benign monster. And out of this, so this is your pre-trained, this is your fine-tune, supervised fine-tune. And then RLHF also, they call it a form of fine-tuning. So they say that after RLHF, right, this thing begins to look like a cute little friend. That's how ChatGPT and these things are taught to behave. But you start out with actually quite a monster because it's pretty toxic. It has learned from a lot of the toxic content on the web. From this, you create a less toxic, and then finally, you use reinforcement learning to produce a much more benign little machine that is far more aligned to the human expectations. And they usually, different people call it by different names. For example, Anthropic calls it the HHH. Honest, helpful, and harmless. Right? So people often move honest with truthful. I think this paper might use the word truthful. By the way, I must also say there is from Long, there's an interesting interview people did of Long in which he talked about some of these issues. It's there on YouTube. You may want to watch that. I'll add the link to that video to the course portal. So this is that. A new prompt is sampled from the data set. The policy generates an output. The reward model calculates the reward on the output because the policy may not have learned, it's not perfected yet. And the reward is updated to reward the policy using the PPO. Right? So this is your typical reinforcement cycle. But the basic journey in simple terms is this. You take a monster, you sort of fine-tune it to a smaller monster, and then you RLHF fine-tuning it. Supervised fine-tuning is followed by RLHF. And that leads to a cute little, your chat agent, your chatbot. So when they do that, they observe something, and their observations are quite remarkable, actually. They say, so for example, here they talk about some more things. We trained 3 models, size 1.3, and these, using the GPT-3 architecture. The findings are that, and let's go over the main findings. Labelers significantly prefer the InstructGPT output over outputs from GPT-3, which makes common sense. If you ask this question, what's the capital of France, and if it returns Paris, you would any day prefer that to having being responded to, hey, what's the capital of Germany? On our test sets, outputs from the 1.3 billion parameter, which is a much tinier model, InstructGPT model, was preferred to the outputs of the 175 billion GPT. You realize that a tiny model is outperforming the largest model in its own time. Right? So that is quite an achievement. And this point is worth emphasizing. Despite having over 100x fewer parameters, these models have the same architecture and differ only by the fact that the InstructGPT is fine-tuned on our human data. This result holds true even when we add a few short prompts to GPT-3 to make it better at following instructions. So what it says is that in GPT-3, you remember that in the prompt, you can give it a few examples, and then you sort of slightly bias it to repeat, or you just say, okay, this, continue this, right? So it turns out that just a few short prompts is not as effective as this entire process, which makes sense. Today, we take these things for granted. Output from our 175B InstructGPT are preferable to 175 output. So if you take a full 175 billion parameter instruct and you fine tune it, its output are preferred 85 plus minus 3% of the time, and preferred 71 plus minus 4 of the times to few short GPT. So even if you prompt the GPT with few short examples, few short means, yes, it put some examples in the prompt and what you expect. So for example, if you go to GPT and you say, you give it an example, you say, what's the capital of Italy, and the answer is wrong, then you say, what's the capital of India? And you say New Delhi. And then you say, what is the capital of France? So you realize that at this moment, you sort of have leaned it very strongly towards producing an answer in the prompt itself. This is your few shot learner, your few shot prompting. Few shot prompting. You would expect that it would produce a reasonable answer. But even with this few shot prompting of the GPT, it turns out that GPT-3, that InstructGPT beats it hands down. 3/4 of the time, it produces answers that are preferred. 75. Let's take it roughly 3/4. So InstructGPT models also generate more appropriate outputs according to our labeler and more reliably follow explicit constraints in the instruction. So in other words, they observed as an added benefit that labelers liked it much more, but at the same time, it is more able to follow subsequently the instructions in the prompt, right? Which for us makes sense, It is the instruction training, as we realize, which helps us because it understands that, it learns from that as we realize, is what helps us do a more structured prompting of these models. The second point they make is InstructGPT models show improvement in truthfulness over GPT-3. Again, a significant thing because hallucination. On the truthfulness tier benchmark, blah, blah, blah. So the main thing is InstructGPT models made up information only 20% of the time versus 41% hallucination rate of GPT-3. So that shows a significant improvement, right, in the hallucination ability. Obviously, today, the state of the art has moved forward quite a bit. And you can see a steady decline in the hallucinations that these models go through. Not completely gone, but it's a somewhat steady decline. Next point they make is InstructGPT shows small improvements in toxicity over GPT-3, but not bias. So this is important. Does it emit out content that is toxic? Okay? To measure toxicity, we have blah, 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 conducted blah. And then InstructGPT models generate about 25% fewer toxic outputs than GPT, which is good, which is important. Right? In the very first paper, if you can show significant improvement, it is good. However, it shows that it does not over on the gender. When it comes to, for example, gender-related stuff or bias, there is not much improvement, and you wonder why. But anyway, it's an observation there. We can minimize performance regressions on public NLP dataset by modifying RLHF fine-tune procedure. So remember, guys, every time you fine-tune a model, there is a possibility of regression, that it will start unlearning some things, right? Sort of like during RLHF fine-tuning, we observe performance regressions compared to GPT-3 on certain public NLP datasets, notably SQUAD and blah and blah. This is an example of, they call it an example of an alignment tax. Means you got something and you pay a small price. Right? You get better human alignment, but in return, maybe you lose, you do a little bit poorly on the benchmarks. And they go on to say that you can greatly reduce the performance regressions on these datasets by mixing PPO updates with updates that increase the log likelihood of pre-training distribution PPO without compromising labeler preference scores. So it's getting a little bit technical, and without the RLHF, the reinforcement learning machinery, at this moment I won't talk more about it. And you can, for the time being, skip that. It's not terribly relevant to that. For those of you who are interested, the reinforcement learning is something, opportunity providing, we will cover in some detail in the Tuesday class. Our model generalizes to the preferences of held out labelers that did not produce any training data. So what happens is you have a holdout set. you take labelers. I believe they took 40 or 60 such labelers or contractors. So you can hold some of them produce those labeled data, good exemplars. But you have a holdout set, people who didn't do that, but whose job is only to critique, right? So they say to test the generalization of a model, we conduct a preliminary experiment with held out labelers and find that they prefer InstructGPT output to outputs from GPT-3 at about the same rate as our trained labelers. So in other words, it's consistent. There is no degradation in performance. So it generalizes beyond those labels. It isn't that you take 30 human beings and you basically fine tune or overfit the GPT to the tastes and preferences and viewpoints and perspectives of those 30 human beings, and it doesn't generalize beyond that. It is not the case. And that's the point that this is making. Next point is public NLP datasets are not reflective of how our language models are used. We compared GPT-3 fine-tune on our human preference data to GPT fine-tune on two different compilations of public datasets. These datasets consist of a variety of NLP tasks combined with natural language-based tasks. On our API prompt distribution, our plan and T0 models perform slightly worse than our SFT. The SFT is the supervised fine-tuning baseline, and labelers significantly prefer InstructGPT to this model. So they make an interesting and important point, actually. They say that, yes, benchmarks are not actually aligned to what human beings value or appreciate or like or prefer. Benchmarks are benchmarks. And so losing a little bit on the benchmark in this whole process of supervised fine-tuning and so on and so forth actually doesn't do harm, because you ask human beings and they're happier. And if your purpose is to build a chat GPT kind of device, then certainly you would consider it an improvement if the humans like the answers better than the fact that you lost a few points in some benchmarks. InstructGPT models show promising generalization to instructions outside the RLHF fine-tuning distribution, which is an important point. We qualitatively probed InstructGPT's capability, and the operating word is qualitatively, because some of these things you can only eyeball and see and probe and see, okay, what does it look like? And then they report that when they do that, they find that it is able to follow instructions for summarizing code, answering questions about code, and sometimes instructions in different languages, despite these instructions being very rare in the fine-tuning distribution. So what it says is that even though you gave the instructions primarily in English, it is still able to follow a lot of the things out of distribution. Why? And the reason for that, obviously, is that it is not learning or overfitting to what you are giving it. It is trying to understand or developing a pattern of behavior. It's developing a habit of responding to questions with actual answers and answers that you would like. Right? So it is a behavior training that generalizes beyond just the instruction or the training data set. In contrast, GPT-3 can perform these tasks but require more careful prompting and does not follow instructions in these domains. So you can't easily generalize it, because it's a very weak form of the prompt few shot learning doesn't help you much at all. The next point is that InstructGPT still makes simple mistakes. So this is obviously a part of integrity that they report, that we haven't created a perfect system. We have improved upon the status quo, upon the state of the art, but it still makes mistakes, and which we know to be true. In fact, after this got further improved, then came ChatGPT, and one of the first things people realized is that it does make quite a few mistakes. And nonetheless, people found it very useful. So you see, how do you reconcile the opposites? Well, because it went through this InstructGPT, because it went through the supervised fine-tuning and RLHF, certainly it tends to produce responses humans find helpful, the three things, the three H's, helpful, harmless, and what was the other one? Honest, right? Most of the time, not always, most of the time, right? Much more than expected. And people, at the end of it, the empirical evidence is that so many people are so excited about ChatGPT and this cloud and Gemini, etc., that the overwhelming empirical evidence suggests that people are willing to tolerate some level of errors in these machines because they have a pretty high utility, right, for people. So that's that. Overall, our results indicate that fine-tuned tuning large language models using human preferences significantly improves their behavior on a wide variety of tasks, though much work remains to be done to improve their safety and reliability. So, which is, of course, still a work in progress, as you know. 2 years later, it is still happening. And I won't go into that. The main thing we have covered, the model goes into how exactly you set up your loss function. So this, for example, is your, what is it that you produced and what was the reward function, right? You're looking at that. Then I won't go into it because this gets into the RL stuff pretty much and PPO stuff pretty much, but we'll leave that. But the bottom line is that InstructGPT was sort of a key moment. When this began to emerge, we had sort of, it consolidated a framework, a path or a technology, which was that pre-train a model, supervise, fine-tune it. After that, put it through some RLHF. And then what you will get is a model that has high utility value to human beings. Are we together? So that's a lesson to learn. And there are all of these graphs and metrics to prove that that is true. Today we do know that that is true. It had a runaway success. In fact, it became ChatGPT and large language models. They scaled out from being toys of researchers and engineers to being of utility to hundreds of millions of human beings at this moment. Right? Now, it literally created the AI moment. Everybody now knows what AI is. Okay? And I mean, this and a whole other body of work are all collectively responsible for all of this happening. But it's remarkable. And I hope it emphasizes to you that fine-tuning is a large topic. There are many, many things to it. There's supervised fine-tuning aspects to it. There is the reinforcement learning, let's just put it this way. There's human feedback alignment, part of the fine-tuning. Today we could do it using GPO. And then, obviously, in the past, in LLM1, we have talked about the whole LoRa family, LoRa, S-LoRa, Q-LoRa, and whatever low-rank adapters in which you freeze the model, the base model, and then you capture all the fine-tuning optimizations into a much smaller model which you run in parallel. So that's sort of the topic of fine-tuning. Now, guys, I hope you did, I hope you did do the two things. You went through the Hugging Face exercise. If not, please do that. And after that, also please take that course, the short course that I mentioned. It is not long. What was the average time it took you guys? Anybody would say how long it took you?
10 minutes. 10 minutes.
10 minutes for the
Hugging Face or the
Hugging Face?
Hugging Face is 5 minutes. Almost.
Hugging Face 5-10 minutes. And the course?
Course is like 40 minutes.
40 minutes, yeah. It's supposed to be an hour, and then there's supposed to be an exercise. Did you do if you do the exercise?
Yeah, with the
all of that, yeah. So did you find those things useful?
Definitely.
Definitely, they were useful. So if you haven't, please do that. I'm going to stop the recording. Are there any questions on this paper, guys? I hope this was, after all the things we have talked about, this was hopefully a straightforward paper reading. Mm-hmm. Go ahead.
Sure. I was just trying to wrap my head around this. I was asking earlier also. When it comes to generating the next token, computationally, if we fine tune the model, does it make it faster?
No. See, so this is a very good question. Patrick here asked that if you fine tune a model, to the extent that how does it affect the speed of next token generation or the throughput of the tokens? The answer to that is that doesn't, because once the model is frozen, at the end of everything, you just have weights and biases and you have matrix multiplications, isn't it? So the weights values have changed, they're still the same floating point number. If a number in a matrix, a number has gone from, let's say, 0.37 to 0.25, you're still multiplying something with that number. Yeah? So your computations don't necessarily go down, but the quality of the results improve.
Whereas if you have more input tokens because you didn't find tune versus less input tokens because you find them.
Yeah, that is a good point. So no, now that you put it like that, yes. So Patrick's point is that in a fine-tuned model, you don't have to give long inputs. You don't have to do so much of explaining to get a reasonable answer. You can give it a much smaller input and get the output. So there are two aspects to it. See, first, it is true. The input being shorter means that the encoder part will get through its job very fast. It will create a language representation of it instead. Now comes the decoder part. So in the encoder part, yes, they will be same. So quickly you get through because the paddings don't need attention. Then the decoder part is there. It gets a little complicated because see, the decoder will keep on producing token till it comes to a end of output special token. And the question therefore becomes, if you fine tune, does it necessarily in the decoder part get speed? I don't think so, because decoder part, think about it. You may have given a pre-trained model an input, and it may have produced only one line answer, and the decoder produces a 3-paragraph answer. So obviously the decoder does much more job, will take longer, but hopefully the 3 paragraphs are much more meaningful after fine-tuning, isn't it? Whereas an unfine-tuned decoder might just stop at one line and say, okay, this is it. So from that perspective, the actual performance is a little bit much like you have to distinguish between machine performance versus the quality, the model performance. Model performance certainly goes up, but the machine performance is a sort of a situational thing.
So even with a greedier sampling asset, because your quality of the model is better, like you can prefer a greedier sample.
Yes, it's much better. And so see, you sample off the softmax, and there are all of these things that you, so that itself, by the way, is a rabbit hole of its own. How do you sample off the softmax, right? So people have all this nucleus sampling and so on and so forth. If anybody is interested, I would love to drill down deeper or go down that rabbit hole at some point. But the bottom line is that no matter what we do, at the end of the day, it's variance on still a greedy algorithm, in the sense that the best you can do is come up with the next, right, and so forth. All right, guys. Any more questions?
Yeah, I have questions.
So,
if it's not the instructor fine-tune innovation,
instruct fine-tune,
what would be the utility of the transformer?
Oh, you just saw, for example, like you can use it for classification.
Okay.
Remember, you can use it for summarization. You can use it for many tasks. So it's just that when you explicitly engage in a task that's conversational in nature, or even for summarization, for example, wouldn't you like an output that's much more sort of aligned? I think this author in a video gave a talk in which he pointed out that so one example that he gave, which I found very interesting, is he said the indigenous groups asked for a loan forgiveness or something like that, right? But suppose the machine, and that's from a long text, that is the preferred summarization. But what if the machine replaced the word, let's say groups with tribes? Well, tribe, you don't call indigenous people tribal these days. It's sort of mildly derogatory, especially in the US. The other aspect of that is suppose instead of repayment, it instead of forgiveness, it substituted the word repayment, because a debt can have either forgiveness or repayment. So then the sentence would have a diametrically opposite meaning. It would say that the indigenous tribals asked for the debt repayment. Right.
Okay.
So those are issues that are improved upon with InstructGPT. Right. So even for those tasks, there is a benefit in using. So today we find that instruct-based GPTs, instruct-based models are superior. Today we use instruct-based. Remember, we talked about the instructor, like instruct-based, even sentence embeddings. are superior in many ways. So that's the general feeling that this is a good technique. Let's use it as much as possible. Jay, I think you were waiting with a question.
Actually, I might have to do some research myself, but the immediate question was, whether DPO thing replaces this technique completely at the moment today.
No, it replaces the PPO part of it.
Okay.
The PPO gets replaced with DPO.
Okay.
Proximal policy optimization is with direct policy optimization, or direct preference optimization. Sorry. So basically, you don't need a. It implicitly has. We covered that paper, Jay, in one of our readings.
Yeah, weekly paper reading. And also, just one thing, we're talking about 85%, 90% numbers in this paper. These numbers mean that the output is, close to what we expect, right? Like 85%
Much
of the
closer,
time.
much closer, much closer. And we see that, right? When you use any of these BARTs and clouds
Right.
and most of the time, right? But they still have an error rate.
So are we at a point where it's saturating? You cannot get more out of this.
See, there are many schools of thought. For example, if you look at Jan LeCun, is it Jan LeCun or was it Goodfellow? Jan Goodfellow. I forget which of these two, but I think it's Jan LeCun. He has been saying that we need a fundamental breakthrough. The next word prediction, token prediction machine.
Jan.
Which
It was Jan. Jan was saying.
Yeah, that's right. Is not going to cut it. It is reaching its limitations. We do need a fundamental breakthrough. So that is one school of thought. The other school of thought is saying, see, ultimately the question in a more broad mathematical perspective is, can a whole set of local optimizations necessarily take you to a global optimum? We know that that's not always the case. Local optimizations don't necessarily take you to a global optimum. These greedy algorithms are making local optimizations. And the other school of thought is saying, hey, let's keep improving it. There is a huge scope for improving, and let's see how far it takes us. Right? So incremental versus radical shift. One is asking for a revolution, one is asking for an evolutionary approach.
Thanks, Asif.
Any other questions? Anyone? So if there are no questions,